Picture the irony. A city built in the middle of one of the planet's largest deserts forced to import sand. Yeah, you heard that right. Dubai, surrounded by billions of tons of golden dunes, buys sand from overseas. I'm standing on the edge of the man-made Palm Jumeirah island, and beneath my feet isn't Arabian desert sand, but carefully calibrated, washed, and sorted material that arrived here from the ocean floor hundreds of miles away. The sun beats down so hard the air above the asphalt shimmers, and the Persian Gulf humidity turns every breath into a struggle. But right here, between luxury hotels and turquoise water, one of the Middle East's most massive industrial operations unfolds. Welcome to the Dubai Marine Aggregates plant, where the ocean floor becomes paradise beaches. Dubai's problem is paradoxical and brutal at the same time. The desert sand surrounding this city on all sides is completely useless. Billions of years of wind have polished each grain to perfect roundness. Under a microscope, desert sand looks like glass marbles, smooth, polished, beautiful. But it's precisely this beauty that makes it unfit. Round grains don't bind to each other. Try building concrete from them, it'll crumble. Try creating a beach. It'll wash into the sea with the first wave. Desert sand is like trying to build a house out of glass marbles. Ahmed, the plant's chief engineer, explains to me, squinting in the sun. We need sand with sharp edges, angular, rough. We need marine sand. And that's why Dubai, sitting on an ocean of sand, sends giant dredges to the bottom of the Persian Gulf. Every year they pull up millions of cubic yards of seabed sand, which then goes through an incredibly complex processing operation. This isn't just extraction, this is surgery at the molecular level. We're boarding the dredge Al-Muharraq, a floating factory 400 feet long. This isn't a ship, it's an industrial monster. I feel the vibration of massive diesels driving pumps that move 15,000 cubic meters per hour. A suction pipe 4 feet in diameter descends 80 feet down to ancient deposits of shell rock and coral sand. Captain Saleh, a man tanned almost black with wrinkles as deep as cracks in stone, points me to the echo sounder monitor. See that line? That's a layer of quality sand. For millions of years, the waves of the Persian Gulf crushed corals and shells. What wind did for the desert over billions of years, the sea did in millions, but the result is opposite. When the suction pipe touches bottom, the sound changes. Before it was the monotonous hum of the pumps, now there's a grinding added. Sharp fragments of shells and corals flying up through the pipe. A mixture of water and sand in a ratio of 1 to 5 rises to the surface. Here on the dredge deck, the first stage of processing begins. The pulp, that's what they call this dirty, murky mixture, feeds into the primary screen. It's a vibrating steel table the size of a tennis court, covered with a mesh that has quarter-inch holes. Here's where the big chunks get filtered out. Coral fragments, shells, sometimes even pieces of sunken ships. The fine fraction falls through and enters a cascade of washing drums. The water here is seawater, but it runs through a filtration system. 3 massive cylinders, each about 13 feet in diameter, rotate at 20 revolutions per minute. Inside them are spiral blades that churn the sand and water so intensely that every grain of sand gets mechanically cleaned. Salt, organics, silt, it all washes away. I watch as dark brown sludge comes out of the first drum, light gray from the second, and from the third, nearly clear water with clean sand at the bottom. The temperature inside the drums hits 113 degrees Fahrenheit because of friction. This isn't just washing, it's thermal disinfection. Any organic residue, bacteria, algae, they all die in this hot whirlpool. After washing, the sand moves to hydrocyclones, devices that separate material by density and size using centrifugal force. Picture giant metal cones 20 feet tall. The slurry gets pumped in at a pressure of 8 atmospheres. Inside the cone, it starts spinning at 300 revolutions per minute. Heavy particles, coarse sand, and small pebbles get pressed against the walls and sink down. Light particles, silt, clay, very fine sand, get carried upward by the rising water current and get dumped as waste. I walk up to the outlet of the lower stream. Coming out here is sand ranging from 0.02 to 0.05 millimeters, the perfect size for beach sand. If the particles are smaller, they turn to dust and blow away in the wind. If they're larger, walking barefoot on that sand is uncomfortable. It cuts your skin. Ahmed grabs a handful of wet sand and holds it out to me. It's heavy, dense, and every grain has an irregular angular shape. Feel those sharp edges? That's coral and shells. They lock together. Waves can't wash this sand away. It creates a stable surface. The next step is desalination. Even after 3 wash cycles, sea salt remains in the sand. If you don't remove it, within a few months the beach will be covered in a white film, and any nearby metal structures will start rusting twice as fast. The sand goes into long troughs where it's flooded with pressurized freshwater. It's expensive. Every 1,000 cubic meters of sand requires 200 cubic meters of desalinated water. But in Dubai, water is valued more than oil, and the plant has its own reverse osmosis desalination unit. The process takes 4 hours. The sand slowly moves through a trough about 500 feet long, while pressurized freshwater, at 3 atmospheres, pours down from above. The salt washes out, concentration drops from 35 grams per liter to 0.5. The plant's lab constantly takes samples. They're not just checking salt, but pH levels, heavy metals, organic contaminants. The standards are strict. This sand is going to touch the skin of thousands of tourists. Kids will be crawling on it. One mistake and the beach's reputation collapses. Now for the really interesting part, color and texture calibration. Natural Persian Gulf sea sand has a grayish-white tint. It's beautiful but not postcard perfect. Tourists want to see golden, warm, almost caramel-colored sand, like in the Maldives or Thailand. And this is where the alchemy begins. In a specialized facility, the sand is mixed with mineral additives. This isn't paint. These are crushed natural minerals. Iron oxide gives a reddish tint. Dolomite flour, creamy. Quartz dust, a golden shimmer. The proportions are calculated by computer based on samples of perfect beach sand from around the world. Engineers loaded into the database photographs and physical samples of sand from Bora Bora, the Seychelles, Zanzibar. The program analyzes color temperature, brightness, saturation, and produces a recipe. For Palm Jumeirah, the recipe is this: 92% base sea sand, 5% dolomite, 2% crushed yellow quartz, 1% iron oxide. Mixing happens in drum mixers with a volume of around 1,750 cubic feet. The drum rotates for 20 minutes, ensuring absolutely even distribution of the pigments. The final stage is heat treatment and stabilization. The sand is dried in rotary kilns at 250 degrees Fahrenheit. This kills off the last bacterial and fungal spores and activates the mineral bonds between the additives and the grains. The color gets baked in and becomes UV resistant. After the kiln, the sand is cooled and treated with a silicone-based hydrophobic compound. It's a thin, invisible layer that makes the grains slightly water repellent. Why? So the sand dries faster after rain or waves, doesn't turn muddy, and doesn't form puddles. This is Dubai Marine Aggregates know-how: self-cleaning sand. The finished product gets loaded into dump trucks and shipped to the beaches. But that's not the end of the story. Every beach has a monitoring system in place. Sensors buried at different depths measure moisture, temperature, sand displacement. If a storm starts washing away the surface, they truck in a fresh batch right away. Twice a year, all the sand gets sifted by special machines, removing trash, seaweed, shell fragments. It's a living system that requires constant care. I'm standing on Jumeirah Beach watching a wave roll onto the shore and retreat, leaving behind a perfectly smooth, slightly damp surface of golden sand. Beneath my feet, a pleasant coolness. The sand has already dried since the last wave. No clumps, no mud, no sharp shells. Each grain of sand has traveled from the ocean floor through washing, sorting, dyeing, and heat treatment. This isn't nature. This is an industrial symphony where technology creates the illusion of pristine wilderness. In Dubai, even the sand is a high-tech product. A city in the desert that imports sand from the ocean floor, processes it in factories worth billions of dollars, and creates beaches that look more natural than nature itself. This is Dubai, a place where reality surpasses imagination, and human ingenuity defeats the laws of geography. If you found it interesting to learn how Dubai's perfect beaches are created, give this video a like. Write in the comments what beaches around the world you visited and which sands seem the best to you. And subscribe to the channel to keep discovering the amazing technologies hidden behind the everyday things in our world. What if the most dangerous part of a suspension bridge isn't what you see? Because inside the main cables, which look like solid metal, there's a structure made of tens of thousands of wires, each one vulnerable to destruction by even a drop of salty fog. So why doesn't a bridge weighing thousands of tons collapse every single day? And what happens if moisture gets inside the cable where nobody can see it? The Golden Gate Bridge in San Francisco has two main cables, each about 37 inches in diameter. Inside each one, 27,572 individual wires. If you unwound all these wires and connected them into one line, you'd get roughly 80,000 miles of steel. That's about 3 times the length of Earth's equator. The weight of just one of these cables? Around 24,500 tons. That's comparable to the mass of a small cruise ship. Japan's Akashi Kaikyo Bridge, one of the longest suspension bridges in the world, has main cables made of many thousands of high-strength steel wires. Their combined length exceeds several tens of thousands of kilometers. Stay till the end. You'll learn a secret that even bridge engineers don't talk about. Picture the classic example, San Francisco's Golden Gate Bridge. It's got two main cables draped over towers and anchored into massive concrete blocks in the rock. Each cable's about 37 inches across. That's not a cable anymore. It's practically a pillar you'd need 2 or 3 people to wrap their arms around. Inside, 27,572 individual wires, compressed into a perfectly round bundle. Unwind all those wires and link them end to end, and you've got roughly 80,000 miles of steel. That's about 3 times the length of Earth's equator. One cable weighs around 24,500 tons, comparable to a small cruise ship or several hundred fully loaded semis. Why so many wires instead of one giant solid rod? Steel handles tension beautifully, but it doesn't tolerate flaws well, especially in large cross-sections. When a cable is made up of thousands of individual wires, each one can give a little, taking on a bigger share of the load in some spots, a smaller share in others. If one wire happens to corrode or weaken for some reason, its contribution to the overall strength is minimal, and you won't even notice it in how the whole cable behaves. Plus, it's way easier to create a flexible shape out of tens of thousands of thin elements. A cable can smoothly wrap around towers, forming a big parabola across the span, whereas a solid rod of that diameter just can't be bent without permanent deformation. The process of making the main cables for a suspension bridge is nothing like how regular steel cables are made at a factory. Nobody ships a pre-made coil a yard thick and thousands of feet long to the construction site. A monster like that would be impossible to deliver or lift into position. So the main cables of suspension bridges are spun on site. It starts with installing temporary working cables between the towers. They run a traveling cart along them that can zip back and forth across the entire span. The cart carries a coil of steel wire. Each trip of the cart means threading another wire between the shores. One end of the wire gets fixed to an anchor on one side. The cart hauls the coil across the span. The wire gets secured on the other shore, and the excess gets cut off. Then the next wire, and so on, tens of thousands of times. To keep this insane marathon from turning into chaos, the wires get organized into what are called strands or subcables. For example, several hundred parallel wires get bundled into one strand of a specific diameter. First, all the wires get tensioned with a little slack. Then special jacks even out the tension so each little wire carries roughly the same load. Then the bundle gets clamped with rings or special bands to keep it from spreading apart. When there are enough of these bundles, they get brought together and compressed again into a single cylindrical structure. A spiral wrapping of thin round wire goes on top to hold the shape, plus a protective layer of paint or other anti-corrosion coating. At this stage, the cable can already hold incredible force. Picture a bridge deck suspended from it, a steel truss or box girder carrying the road surface. This deck structure transfers the load to the main cables through suspenders. Any vehicle crossing the bridge adds several tons to the system, sometimes dozens if we're talking about a semi or multiple trucks together. Wind pushes against the side of the structure with a force that can reach thousands of kilonewtons during a storm. Ultimately, the main cables feel all of this, stretching literally just a few inches along their entire length while staying within the elastic range. The beauty of a suspension bridge is that the cable works purely in tension, not bending or compression. That's the ideal mode for high-strength steel. The modulus of elasticity and tensile strength of these cables are specifically chosen so that working stresses stay well below ultimate limits, even accounting for wind gusts, temperature swings, and heavy traffic flow. During the design phase, engineers model every possible loading scenario. Both lanes completely filled with trucks, sudden braking, seismic events. The result? An acceptable range of cable elongation and sag within which the bridge remains safe and comfortable for users. Here's the fascinating part. Despite all that rigidity, the main cables aren't absolutely static. They breathe with the bridge. On a hot sunny day, the steel expands and the cable sags slightly. At night, as temperatures drop, tension increases and sag decreases. In windy weather, you might notice a gentle oscillation in the deck. The cables themselves are actually moving too, though it's invisible to the naked eye. It's precisely this living, flexible behavior that allows suspension bridges to handle dynamic loads better than rigid, overly stone-like structures. Excessive rigidity is exactly what led to disasters in bridge building history, while controlled flexibility allows the dissipation of vibrational energy. A separate critical topic: protecting cables from corrosion. Steel fears moisture and salty fog, especially in coastal regions like San Francisco. If water and aggressive contaminants get inside a cable, reaching each of the tens of thousands of individual wires, corrosion can silently eat away the cross-section for years until it's too late. That's why immediately after strand spinning and compacting are finished, cables get sealed. First thoroughly painted, then the coating is periodically refreshed. Modern bridges employ additional systems, wrapping with airtight tapes, filling gaps with dehumidified air or nitrogen, monitoring humidity inside. Regular inspections are conducted, including magnetic or ultrasonic non-destructive testing methods, which allow engineers to understand the condition of the wires without opening up the cable. All of this is done so that a single strand of infrastructure can safely serve for decades. The cables of the Golden Gate were designed for a service life of tens of years, but thanks to proper maintenance, regular repainting, and monitoring, they still do their job today, holding up the main span of over 4,000 feet. If you add in other suspension bridges around the world, the picture becomes even more impressive. Hundreds of thousands of miles of steel wire stretched across rivers, bays, and straits, keeping millions of cars suspended in the air every single day. Using main cables made from thousands of steel wires is standard practice for large suspension bridges, so the Golden Gate isn't alone here. One of its most famous relatives is the George Washington Bridge across the Hudson in New York. It also has two main cables woven from tens of thousands of steel wires. The total length of all that wire is measured in thousands of miles, and the mass of each cable runs into tens of thousands of tons, just like the Golden Gate. The same technology was used on the Brooklyn Bridge, though it's older and combines a suspension system with cable stays. There, the main cables also consist of a large number of thin wires spun on-site rather than brought in as pre-made rope. Modern giants are built using the same principle. For example, Japan's Akashi Kaikyo Bridge, one of the longest suspension bridges in the world, has main cables made from many thousands of high-strength steel wires. Their combined length exceeds several tens of thousands of miles, and the design tension reaches hundreds of thousands of tons. A similar approach is used on numerous bridges in China and South Korea, which have been actively building long-span crossings over bays and wide rivers in recent decades. All these bridges share one technology. The main cables are spun on-site from tens of thousands of individual wires, each one tensioned, aligned, and compressed into a unified structure. This technology creates cables of incredible strength and flexibility, capable of holding thousands of tons and handling dynamic loads from wind, traffic, and temperature changes. And so, traveling from a coil of steel wire through tens of thousands of trolley trips across the void, through hydraulic jack tensioning and compression into bundles, through wrapping with protective wire and coating with anti-corrosion paint, the main cable of a suspension bridge is born, a structure of 27,572 individual wires, weighing 24,500 tons, able to stretch several inches under load but staying within elastic deformation, holding in the air a bridge over 4,000 feet long, carrying millions of vehicles every single day. Each wire is a separate element, and if one weakens, it's barely noticeable to the whole system. But if moisture and salt get inside, corrosion can silently destroy wires for years. That's exactly why modern bridges are equipped with humidity monitoring systems, regular inspections, and non-destructive testing. So these giants of steel and concrete can safely serve humanity for centuries. You're holding $100 in your hand, a green piece of paper with Franklin's face on it. Light, thin, looks ordinary, but it's not paper, and it's not ordinary. This bill was printed in a building guarded better than the Pentagon. Cameras everywhere. Motion sensors. Armed security. Getting in there is harder than getting into Fort Knox. The paper for it was made using a secret formula. 75% cotton. 5 people in the world know the formula. Printed 3 times. Each time with different inks. Each time with precision down to a micron. One wrong stroke, and the bill is counterfeit. Checked by machines. Every millimeter scanned. Rejects burned immediately. Not even one bad bill gets out. Because if it makes it outside, someone could forge it. This piece of paper is protected better than a vault in a bank. Watch till the end, you'll learn how money is printed. And you'll never look at a dollar as just a simple piece of paper again. Texas. Cotton fields stretching to the horizon. Heat pushing 100 degrees. White cotton bolls bursting on the bushes. Combines harvesting the crop. But not all cotton makes the cut for money. Only the longest fibers. White. Strong. Hand-selected. Shipped to the factory. Massachusetts. Town of Dalton. Crane Currency Facility. They've been making paper for dollars since 1779. Nobody else in the world has the rights. The grounds are guarded around the clock. Airport-level security screening. Cameras in every corner. Cotton gets mixed with linen. Boiled in massive vats. Water added. Creates a white pulp. Rolled into thin sheets. During the rolling, red and blue fibers get woven in. Randomly. Chaotically. Impossible to replicate the pattern. First line of defense. Then a security strip gets embedded. Thin metallic thread, glows under ultraviolet light. Water pressed out, dried. Cut into large sheets. Every sheet inspected against the light. Checking for defects. One air bubble. Sheet gets rejected. Finished paper gets packaged. Transported under convoy. Armed guards. Armored truck. Because if someone steals this paper, they can print real money. Washington, D.C. A building with no signs. Gray, nondescript. Inside, they print money. Bureau of Engraving and Printing. Security level like a military base. Metal detectors, retinal scanners, fingerprints. Even employees can't enter without triple verification. Cell phones banned. Cameras banned. Any recording devices confiscated. Inside, printing presses the size of a bus. Each one costs $10 million. Running around the clock. Sound like a jet taking off. Paper loaded in stacks. 32 sheets per stack. Each sheet will print 32 bills. First pass, background printing. Green patterns, fine lines. Hand drawn by engravers, for months. One mistake, start over. Lines so fine they're invisible to the naked eye. That's the second anti-counterfeiting measure. Special ink. Formula classified. Made at a different facility. Under the same level of control. Sheets pass through the printing cylinder. Come out green. Wet. Dried under infrared lamps. Every sheet inspected. Sensors scan color, density, line alignment. Precision. 1/100th of a millimeter. Thinner than a human hair. Second pass. Intaglio printing. The most important one. Franklin's portrait, the numbers, the text, all of it printed under massive pressure. 3 tons per square centimeter. The ink gets pressed into the paper. Run your finger across it, you feel the texture. That's the main security feature. Impossible to fake. Regular printers can't do this, even professional ones. You need a special machine. There are 10 of them in the world, and they're all here. The printing cylinder is covered in microscopic grooves. The design is laser engraved. Precision, 5 microns. That's 10 times thinner than a human hair. The cylinders get replaced every year. The old ones are destroyed, melted down, turned into scrap metal. so nobody can recover the design. Sheets pass through the machine. Come out with Franklin's portrait. Sharp numbers, raised lettering. Another inspection. Machines scan every detail, compare it to the standard. If even 1 pixel is off, the sheet gets rejected. Rejects are set aside separately. Shredded at the end of the day. Burned. The ash dissolved in acid. Even the ash from dollars can't just be thrown away. Third pass, serial numbers. Every bill gets a unique code, 11 digits and letters. This combination doesn't exist anywhere else in the world. Printed in green ink, right side and left side. The numbers must match perfectly. The machine checks. If left and right don't match, rejected. Right then, they print the Treasury seal, green circle, and the Federal Reserve Bank seal, black. The letter shows which bank issued the bill. All of this happens in 3 seconds. The sheet runs through the machine, comes out with numbers and seals. Final inspection, the toughest one. Machines scan the bills under ultraviolet light, under infrared light, under magnification. They check 15 parameters: color, texture, security strip, watermark, line alignment, ink density, size, centering, numbers. Any deviation, rejected. Rejection rate, 3%. Out of every 1,000 bills, 30 get destroyed. Good sheets go to cutting. The rest, into the shredder. Cuts into individual bills. Precision, 1. Cuts into individual bills. Precision, 1/10 of a millimeter. If even one bill is cut crooked, the entire sheet is scrapped. Bills drop into a tray. A robot picks them up, counts them. 100 bills per stack. Wraps them in paper. 100 stacks per block. $10,000 in a single block. Blocks get wrapped in film, sealed, stamped with the date. Serial number, quantity, loaded into safe containers. Metal ones. Locked with 3 separate locks. 3 different people hold the keys. 1 person can't open it. Containers get loaded into an armored truck. Armed guards. 2 escort vehicles. Driven to the Federal Reserve Bank. There they're unloaded into the vault. Underground. Walls 3 feet thick. Steel reinforced concrete. The bills sit and wait until some bank requests them. Then they're pulled out. Counted, packaged, shipped off. Your local bank orders fresh bills. The request goes to the Federal Reserve. From there, they ship a container. Again, under guard. Brink's armored truck. 2 armed guards. GPS tracker, dispatch communication. Any route deviation triggers an alarm. They arrive at the bank, unload into the vault, check the seals. Open the container, count everything. By hand and by machine. The amount must match to the cent. Some bills go into ATMs. An operator loads the cassettes, $4,000 in 1 cassette. Inserts it into the ATM. Closes it up, a TM's ready. You walk up, insert your card, enter your PIN, request $100. Inside, rollers activate. Grab 1 bill, sensors check it. If the bill's wrinkled or torn, the ATM won't dispense it. Takes the next one, feeds it through the slot. You grab it, fold it into your wallet, and walk away. Never thinking about the journey that piece of paper took. From a cotton field in Texas to your wallet. Secret paper, triple printing, 15 inspections, armed guards at every stage. Now you know. This bill isn't just paper. It's the most protected document in the world. It was printed by people who passed security clearances. working on machines worth $10 million. Under cameras and sensors, any mistake, and the bill is destroyed, burned, dissolved in acid, because even a defective bill in the wrong hands is a threat. Someone could study it, understand the technology, try to counterfeit it. That's why the security is so tight. You'll never look at a $100 bill like ordinary paper again, because now you know it has 300 years of technology encrypted in it. Red fibers in the paper are randomly placed. The security strip glows under ultraviolet light. Franklin's portrait is pressed under 3 tons of pressure. Microlines thinner than a hair. Serial numbers unique. This bill is impossible to counterfeit, even if you really try, because it wasn't made to be beautiful. It was made to protect money from counterfeiters, and it works.